Good afternoon. I'm Jessica Mintz. I'm a chemistry teacher at Bayshore High School, and we're going to be reviewing the periodic table. It's a very simple unit, so we're probably not going to be here for the full hour. I've included links for you because I cannot communicate through chat with you. Only you can communicate with everyone around you rather than myself. So I've set up for you a way to send me questions through Remind. So let me pull up that for you so you can see. I'll share my screen with you. And I'll pull up how you can connect. Okay. So here's how you can ask me questions if you want to sign up for my Remind page. All right, so you're going to text at 28F2F, this phone number. And then I can be able to answer your questions live as you send them in. So we already have a couple of questions in, so I will answer those questions as we move through. So I'm going to do this a little bit differently. I know a lot of teachers have been showing you a PowerPoint. At any point, if you need me to post this back up, I will, but it's also in the bottom, in the comments section, the comment section, or the description of what we're discussing today. So you can get this at any point and ask me any questions that you deem necessary. Try to refrain from the interesting chats that are happening as the live feed is going. We put a lot of effort into making sure that you didn't have to leave your home to go through a nice long chemistry review. Keep in mind that all these reviews you can watch later on, and when we're finished, we'll do some Regents practice, and I'm just going to tell you the major things that are important for you for the exam on Tuesday. I'm not going to go into things that are not going to be on the test. So let's make sure we keep it nice and simple for you. Okay, so I've also have some documents down there for you. So what I've done is I've created for you a nice little review for the Regents for your periodic table. So we're just going to go through this, and I'm going to pull up the reference table and refer to how you can use the reference table to help you answer questions on the periodic table. Very simple. And then we'll look at the January exam to try to see how many questions you might come across that are from the periodic table. There's really not that many. So the first thing that I want to discuss with you is the location and the arrangement of the elements on the periodic table. So I'm basically just reading through here, starting at the top, and I'll use my highlighter to kind of point out where I'm at. So here I am right on number 1. So the periodic table is arranged in periods, which are the horizontal rows, all right? And the elements that are in the same row have the same principal energy levels. That's PELs, or sometimes we refer to them as energy levels or energy rings. All right, we're all talking about the same thing. So those are the horizontal rows. So let me pull up the periodic table for you so you can see what we're talking about in live terms. So here's our chemistry reference table. Pardon me while I scroll down, but there we are. So we're talking about the row number, which is these numbers here, okay, and as we go across this way. All right, so everybody in these rows have the same number of energy levels. Now, that's not something that you have to memorize, because what you can do is you can actually look at the electron configuration to help you. So if we look here, I'm just going to zoom in on this one here. And notice if you're in group 3, for example, right, there's 3 numbers on your electron configuration, 281, so that's 3 energy levels, and that happens for all of them within the row. Okay, so you could take a look at that. Okay, as we look at the groups are vertical columns, and the reason why these are important is because the elements that have the same number of valence electrons are in the same grouping, which means that they're going to react in similar ways. And I'm going to pull back up my reference table so we can kind of take a look at that again. But if we look at now the group numbers, right? So if we look at over here, for example, group number 1, and let me just zoom in on group 1 so you can see it a little bit better. Sorry. All right, so here's group 1. All right, and then everything in this group, or the group going down, are going to have the same sort of chemical reactions because of the valence number. So notice that everyone in group 1 has 1 valence number, or 1 valence electron. Everybody in group 2 has 2 valence electrons, which means they're going to behave in similar ways. What's nice about the periodic table is because it is arranged this way, and the group number is telling you how they kind of react, everything in group 1 is going to react similar to each other, which means in the last column, or group 17, they react the same way, in the same manner. For example, fluorine, because it has 1 valence electron, it's willing to lose it, is going to react with lithium, has 1 valence electron, which is willing to lose it, is going to react with fluorine in the same fashion, a 1-to-1 ratio, because fluorine has 7 valence. Sodium, which is in group 1, right underneath lithium, also has 1 valence electron willing to lose, so it's going to react with fluorine in the same way. So sodium to fluorine reacts in a 1-to-1 ratio. So the groups behave the same way because of their valence number. Okay, so let's go back to our review. Okay, so elements in the same group have more similar chemical properties than the elements in the same period because they have the same valence electrons. That's very important as far as the Regents goes. They love asking you about what the groups have in common. All right, they have in common valence number, which means that they are going to react the same. I'm sorry that I did skip this up here, but periodic law actually is going to tell us how the table is organized, the properties of the elements of the periodic function of their atomic number. So as atomic number goes or increases, you're going to see a regular repeating pattern of properties, and we'll go through those transitions in just a moment. But if you look at your table, we read it like a book, right, from left to right, and notice the atomic number increases as we read it, just as we read a book. So the periodic table is organized by atomic number. A question came across about how many electrons are in each shell. This is not something that you have to memorize for the Regents exam. What you can look at is your electron configuration. All right, the electron configuration will tell you how many electrons are in each cell. And we all know that the last group 18 elements are showing complete octets. So you can use that group to kind of figure out how many electrons are going to be held in the first shell, the second shell, and the third shell. So let me just zoom in on group 18 to answer this question. Okay, so here's group 18. And notice, all right, 2 electrons in the first shell. We can just look at neon, for example. 2 electrons in the first shell, 8 in the second shell, right? So that's the full number in each. And if you continue going down, there's the third shell with 8. All right, if we keep going down, 8, 8, 18. So your third shell is a maximum fill at 18, and then you keep filling. All right, so you can use the periodic table to help you in the electron configuration to figure out how many electrons can be held in each cell. The Regents won't ask you this specifically, so you can just look at the configuration to help you figure out how many electrons are in each. Hopefully that answered your question. Okay, so let's go back to my sheet here. And there's some more questions coming in, which we'll go over in just a moment. I hear about nuclear charge and atomic radius coming in. Catlin looks like she sent a question in, so we'll go see that. Catlin or Caitlin? Hopefully you got it right. So let's go down, because I think this is going to answer your questions now that you're asking about why does metallic character increase and why does nuclear charge increase and all that. So let's kind of just go through the representative groups right here. So groups follow trends, groups 1 through 2 and groups 13 through 18. All right, they're going to follow the trends. Transition metals do not follow the same type of trends, group 3 through 12. So the middle of the table don't follow these trends as groups 1 and 2 and 13 through 18. So here are your group names, and these have specific names because they have similar characteristics and react in similar ways. So group 1 are the alkali metals, group 2, the alkaline earth metals, groups 3 through 12 are the transition metals. Now what the Regents loves to ask you about or talk about is colored solutions. So transition metals tend to form colored solutions. All right, so that's something that you should just kind of memorize. Group 17 is the halogen group, and group 18 is noble gases. It's been very rare that the Regents has asked you about the group names. The ones that you should know, though, is you should know transition metals are in the middle, and then you should also know noble gases, group 18. Okay. So we'll get into those trends in just a moment because I'm seeing questions come in about the trends, but I'm going to show you how to use it. So let's just go through number 2, classifying the elements on the table. So the left of the zigzags are metals, to the right of the zigzags are nonmetals, and then on the zigzags are metalloids. Now you should be able to identify these because the Regents likes to ask you about it. So let me pull up my my periodic table for you again, and we can go through this. All right, so I'm going to use my highlighter to show you. Now, what I like to do is actually go through and kind of identify the metalloids first, because we don't want to confuse them as being metals or non-metals. So boron, silicon, germanium, arsenic, antimony, and tellurium are your metalloids that you should know. All right, so when anything to the left of this, so all this over here, and let me see if I can get a different color going here. Let's see. Maybe red. Let's see. So everything over here, oh, perfect. Everything over here are your metals, with the exception of hydrogen. And then I'll color your nonmetals. Oh, let's use gray. Your nonmetals would include hydrogen and then all of these guys over here. All right, so the Regents likes to ask you questions about identifying which of the four has a metal, a non-metal, and a metalloid. So knowing the metalloids is something that you should definitely know. So boron, so basically if you look on the staircase, boron is on the staircase, so B. And then most people know that aluminum is a metal, so even though it's underneath the staircase, aluminum, think of aluminum foil, that's a metal, so that's not going to be a metalloid. Then on the staircase is silicon, and then we go under and over. So under the staircase, germanium, on the staircase, arsenic, under the staircase, antimony, on the staircase, tellurium. So you can just pick them out. Okay, hopefully that was helpful for you. All right, let's go back. All right, so most elements are solid with the following exceptions. So gases, there are 11 gases on the table, so 5 are reactive and 6 are non-reactive. Reactive gases include hydrogen, oxygen, nitrogen, fluorine, and chlorine. The non-reactives are the noble gases, right? So the noble gases, group 18. I'm not really going to ask you about reactivity of these things, but just know that these are the gases. Liquids you should know. Bromine is the only liquid liquid metal, and bromine is the only liquid non-metal, and mercury is the only liquid metal. Now, if you forget these, this is not something that you need to memorize. You can use your reference table to help you. Your reference table can be used by using table S. So let's say you forgot which one is going to be a liquid at room temperature. What you can do is you can go down to table S, and of the 4 choices that they give you, you can look up their melting point and their boiling point. All right, so something that has melted, all right, but not yet boiled is going to be your liquid. So you can use these numbers to kind of help you, and use 273 as your standard in the middle. Hopefully that helped. Okay, so I have some more questions coming in, so let me just pull them up and see what they say, see if they're relevant for us now. All right, and somebody's asking about PO as being a metal or a metalloid. Let's take a look at the table, and I'll pull that up for you. So I think Danny asked this question, so let's pull it up. So here's our reference, right? They're not really going to talk to you about PO or AT, all right? Stop at antimony and tellurium. These are going to be either or. They go back and forth as far as in the chemical community as being either metals or non-metals or metalloids. So for our purposes, let's just stop at the antimony and tellurium. The Regents will not ask you about these bottom 2. In most cases, they're going to focus on boron, silicon, germanium, and arsenic, and they'll probably end up with those 4 as your options. So hopefully that answers your question. And so don't worry about PO, it's not going to be asked. All right, let's keep going. Hopefully you're finding this helpful. All right, so let's talk about reactivity. So francium is the most reactive metal, francium, if that's how your teacher had pronounced it. So what's nice about this is that the way the table is organized, because francium is in our lower left and fluorine is in the upper right, we can talk about being reactive versus the reactivity of each of them. So for example, here's fluorine, francium down here, the most active or reactive metal, very reactive, and fluorine almost on the diagonal, right? Here it is over here. Fluorine is your most reactive non-metal. All right, this happens to be because of their valence number. Again, I doubt the Regents will ask you about that, but just in case, there it is for you. The last thing you should know about classifying the elements are the diatomic elements. And your teacher may have come up with a bunch of different ways to help you memorize these. And this basically is because these elements are reactive that we listed up as gases up here as being reactive gases. They never hang out by themselves. They're always found in pairs. So the reactive or diatomic elements, your teacher may have shown you 7-Up or the mnemonic Brinkelhoff. So I'm going to bring those up so you can see what we're talking about. So I taught my students 2 ways, all right, one using 7-Up, and I'll use my highlighter again to show you what I'm talking about. Let me just change the color to a nicer color. Okay, so starting with atomic number 7, all right, you would draw a 7, all right, which is right there, so you see the 7, and then up for hydrogen. Those are all your naturally occurring diatomics. And what you could do is you could also memorize Brinkelhoff, right, BRINCLHONF. All right, so either way, what's important to remember these don't exist by themselves. They have to be bound to each other. So if you're asked to write out, what oxygen gas would look like, you would have to write it as O2. So I have some questions coming in. So let's just stop for a second, take a look at them. All right, we'll get to Caitlin or Catlin's questions about electronegativity and all that stuff in just a moment. We answered Danny's question, and someone just asked me what's 7-Up. So hopefully with that explanation, that you find that helpful. And whichever one works for you as far as memorizing the diatomics, either using 7-Up or using Brinkelhoff to help you memorize those. And that just means that instead of hanging out by themselves, like just oxygen by itself, you would have to write it as O2. Right, so you wouldn't just write oxygen gas as O, you would write it as O2. Hydrogen wouldn't exist as just H, it exists as H2, okay? All right, let's go back to our review sheet. All right, the term allotrope, right, difference, make sure we talk about difference. So allotropes are 2 or more forms of the same element that differ in their molecules or differ in their structure. All right, so we talk about 2 specific ones. Oxygen, for example, has 2 allotropes. You can have oxygen gas and you can have ozone. They're both made of oxygen, but they have very different characteristics. An easier one to kind of think about is carbon. All right, carbon has a bunch of different allotropes, but let's just focus on these 3. Diamond, for example, and I know most people know what diamond looks like, compared to graphite, which is kind of what your pencils are made out of. They have very different properties, right? Diamond's very shiny, it's sparkly. Graphite is very dull and brittle, right? And coal. So they're all made of just carbon, but yet they have different chemical structures which give them different properties. So those are known as allotropes. I doubt the Regents will ask you the term allotrope. They will ask you about, why these 2 things, O2 and O3, have different properties, and that's because they have different structures, right? Very nice and simple. Give me a moment while we check some of the questions coming in, make sure we're answering everybody's. All right, perfect. Okay, so let's go through some properties of metals and properties of nonmetals. So what's nice is that you can memorize the properties of metals, which are pretty easy because most people know what a metal looks like. So they have luster, which means they're shiny, malleable, which means that they can be bent into shapes. They're good conductors of heat and electricity. All right. Transition metals are much harder than metals in groups 1 or 2. So you may have seen a teacher do an example of sodium, right, a group 1 metal reacting with water. But a transition metal like copper wouldn't react with water. So when your teacher might have shown you that demonstration, sodium they could actually just cut with, they didn't need a knife of any sort or any pliers to kind of get some sodium off. They just needed to they'd probably use their fingers if they wanted to and get it off. I wouldn't suggest it, but it's so malleable in that way. All right. So once you know that the properties of metals, right, have these things, right, the properties of nonmetals are just the opposite, right? So if you memorize the metal properties, right, the opposite of those properties are the nonmetal properties. So they're brittle, they lack luster, right? They're not shiny, they're poor conductors of heat and electricity. Other words that have been used to describe metals, right, luster, malleable, good conductors, we also use metallic, right? Metallic property just means that it has properties of metals, right? They're more metallic. And I know there was a question about metallics, right? They talk about metallic or what does metallic increase or why does metallic properties increase? I'm thinking that that's the question. If you look at the periodic table, let's look at the trend for metallic properties, all right? So your metals are all on this side of the table, right? So over here, right, these are all your metals. So as you move across your table and reading it like you would read a book, going this way, you're decreasing the properties of metal, so you're becoming less metallic, right? So lithium is more metallic than fluorine. Fluorine is a non-metal, right? So non-metals do not have metallic properties. So that's something to consider there. Okay, so let's move on to the periodic trends, because I think this is where most people had the issue. And I'm going to show you some ways to help you with the trends and the questions about trends that you don't have to memorize, right? Everything is on your reference. So hopefully, Caitlin, this answers a lot of your questions about atomic radius, electronegativity, and nuclear charge. Let's talk about each one of these. Remember that you have Table S available to you, and Table S lists for you every element that is on the periodic table that is necessary for the exam. So a lot of the lower, higher numbers are not on there, but everything relevant that what you need is there. And on Table S, you're given the atomic number, the symbol, and name. So you should never guess on this, right? I can't tell you how many people will list sodium as having a symbol S when sodium happens to be Na. So even if you're positive about what the symbol is, maybe check yourself on Table S to make sure you're not making a mistake, because they're given there for you and you don't want to get that point, lose that point. They give you first ionization energy, which we'll talk about in a second, electronegativity, melting point, boiling point, density, and atomic radius on Table S. So what you do need to know about the terms is what they mean. So let's go through ionization energy first. So ionization energy is the amount of energy needed to remove an electron. All right, so when we think about this, if the energy is high, or there's a high number on the energy, that means you would require a lot of energy to take that electron away. Now, elements that want to keep electrons because they're close to having an octet or a stable 8 in their valence number would require a lot of energy to take off their electrons. So, for example, if we look at fluorine on our table, let's pull it up. All right, fluorine is over here. I'm going to zoom in on it if we can. All right, so there's fluorine. Notice 2-7, this is the electron configuration, 7 electrons in the valence shell. Now, when we think about this, fluorine is very close to having an outer shell of 8. It just needs 1 more electron. So it's going to require a lot of energy to get rid of one of those 7, right? The element fluorine does not want to do this. And when I give him personal characteristic, I don't mean him personally, but I just mean that fluorine atom itself is not going to give up electrons very easily. So if we look up the ionization energy for fluorine, right, on Table S, let's find you fluorine. Just zoom in a little bit. Here's fluorine. And ionization energy is the first one, and we can compare it. So here's fluorine. So the ionization energy for fluorine is 1,681. Now let's compare that to, let's say, an element that is willing to give up electrons. So let's go in the same row across and let's look at lithium, right? So I'm just going to navigate across. So here's your fluorine, right? As we go across, here's lithium in the same row. So notice lithium has 1 valence electron. It's a lot easier for lithium to get rid of this electron than it is to gain another 7. So it's not going to require a lot of energy to take this electron off. So when you look at the ionization energy in comparison, it's going to be lower. So notice lithium is 520. So an easy way to remember the trend is, or to look up the trend, is to look up values. If they ask you about going across a row, all right, what you can do is you can go across the row. Hold on, my phone is ringing, I'm sorry. If we go across the row, so here's lithium and we go across to fluorine, what you can do is if they ask you what is the trend of ionization energy going across period 2 from left to right, you can just look up lithium's value and look up fluorine's value. I never use group 18 as far as looking up things, so keep that in mind. So if you looked up lithium, it was 500 something, and you looked up fluorine, it was 1,000 something. The trend as you go across of ionization energy increases, not something that you would have to memorize. Okay, and you can do that for all the trends. So very rarely are you going to have to describe as to why this happens. All right, so ionization energy decreases as you go down a group. So we did across a period, and now let's take a look down a group. So more principal energy levels, far away, less attraction, so it requires less energy to lose electrons. I very highly doubt that the Regents will ask you to explain why the trend goes in one direction in terms of shells. But let's just take a look at that on the table. So if we go down a group, and we can use group 17 again if we want. So fluorine we looked up. Well, let's go down further down to the group. Let's look up iodine's ionization energy and compare it. Where are you? Down towards the bottom. Here you go. So 1008 in comparison to fluorine, which was way up here, 1681. So notice that it is decreasing going down a group. So that's something, again, you don't have to memorize because it's given to you right on table S. You can look it up. Let me just check some of the questions that are coming in to make sure I can answer them as we're going with this spot. So somebody asked about the groups that are transition metals are found, right? They're in groups 3 through 7, groups 3 through 12. So I can pull it up for you just really quick. So your transition elements, sorry, let me clear that off. So here are your transition elements, 3 through 12. Okay, and those are all going to form your colored solutions. Hopefully that answers your question. I think that was Grace. And then let's look at Alexa has a question about ionization energy. Does ionization energy decrease down a group? So yeah, it does. And again, that's not something you have to memorize. Use your reference table to help you with that. As we just explained, going down a group, look up two values in the top of the group and towards the bottom of the group. Okay, all right, so let's go back to our trends, and let's take a look. I'm sorry. Okay. So electronegativity is the attraction for electrons. The larger electronegativity, the more atom attracts the electrons. So sometimes you've seen this in bonding. So when two elements are forming a chemical bond, the one that has the greater attraction for electron pulls the electron closer to its nucleus than the other. So electronegativity, the trend, again, you don't have to memorize, but you can think about it logically. The attraction for electrons, which side of the table wants electrons, right? Again, it has to do with the valence number, all right? If you look at fluorine, fluorine has 7 valence. Do you think it wants electrons or it doesn't want electrons, right? It definitely wants electrons. It's very close to having 8 valence. Whereas if you go on the other side and look at lithium, lithium has 1 valence electron. It doesn't want to attract electrons. It'd rather lose this one. So if lithium forms a bond with fluorine to form lithium fluoride, the fluorine will pull on the electrons more than the lithium, right? So that's the electronegativity. Now, again, that is not something you have to memorize. If you don't know what it is, go down and look up the two values. You can figure the trend as well. So again, use period 2, lithium to fluorine. If you look up their values, lithium is going to have a lower electronegativity, right? Electronegativity of 1, and fluorine is going to have a higher one. So there's your trend. We can also do for the same going down a group. So let's use group 17 again. Let's go from fluorine and let's compare fluorine to bromine. So fluorine has an electronegativity of 4, all right? And if we go down to bromine, bromine has an electronegativity of 3, so the number went down. So there's your trend in ionization energy, and you could do that for both across and down. Okay, and here's your explanation. Again, I don't think the Regents will ask you to explain why the electronegativity trend increases or decreasing depending on where you're going, but here's your explanation. So more principal energy levels, farther away, less attraction, so requires less energy to lose electrons, and it increases you across, more valence electrons as you go across, therefore more attraction, so requires more energy to lose electrons, right? So that's the same thing there. Atomic radius, again, you can do the same thing. You can compare sizes of atoms using table S, but the basic trend is as you go across, and most people can easily memorize this, as you go across, the atom decreases in size because of the strong nuclear pull, right? The charge on the nucleus and the electrons is increasing. And going down, you're getting more principal energy levels, so the atom is getting larger. But again, not something to memorize. Use table S. If you're not sure, take lithium, look up its radius, So it's 130. And if we go across that same period to fluorine, notice that fluorine has a radius of 60. So it decreased. You can do the same going down. So let's go with lithium in group 1, and let's go down right underneath that is sodium. All right, so notice it's getting larger. So lithium is 130, sodium is 160. Right, so that's the trend, not something to memorize. Don't waste your time trying to memorize it when it's there for you. Just look them up. Right, and then the ionic radius, this will be used to actually compare an atom versus its ion. So the distance of the nucleus to the outermost valence electron and ion, you'll be asked to compare atom to its own ion. So let me just pull up an example of that. So if you gain, it equals greater. If you lose, it equals less. So an easy way to kind of think about this is, let's talk about two ions. And I'm just going to zoom in so I can write a little bit better on this. So let's say we had lithium. I don't want my, let's get a pen. So let's talk about lithium compared to a lithium ion. Okay, this is the atom, this is the ion, right? When you compare the size of these two things, the +1 means that you've lost an electron, all right? So because you lost an electron, the atom is larger than its corresponding ion. If you go the other way and we talk about fluorine, right? Fluorine, there's a fluorine atom. Here's a fluorine ion. It's -1. The -1 means it's gained electrons, all right? So in this case, the ion will be bigger than the atom because it has more electrons. Okay, very simple. All right, and the last thing that, I'm not sure if they went into detail about this in previous lessons, but calculating an average atomic mass. And the reason why I have this here is because the periodic table gives you the average atomic mass. So I just thought I would quickly just go through an example in case someone didn't cover it. So any real sample of an element contains more than one naturally occurring isotope. So isotopes, same element, different numbers of neutrons, right? Let's take a look at boron, for example. Boron 10, it's 19.78% abundance, is boron has a mass of 10, and boron 11 is 80.22%, all right? So this is a weighted average. So to figure out the average atomic mass, you would take 19.78 times 10.013 U for atomic mass units, plus the percentage, 80.22% times the mass, 11.0009 U, and then divide by 100. So I've seen it this way, and that's how I taught my students. But you can also write it out this way, where you convert the percentage to a decimal, and that means you don't then have to divide by 100. Okay. Other things I just want to draw your attention to while we're here is the atomic mass unit. So 1 U is equivalent to 1/12 the mass of carbon, 12, all right? And here's how you can memorize this. So notice how they give you the key. So 1/12 of a carbon is 1 atomic mass unit, okay? All right, so some more questions coming in. Let me just check the questions and then we'll move on to some examples. Okay, Danny. When writing charges, what's the difference between writing the symbol in front or behind the number? Well, there is some difference, but we're not going to really go into it because there really is no need to. This is not important for your Regents exam, so we're just going to say whichever way you write it is going to be correct, and let's just leave it at that so you don't have to memorize anything else for your exam. Okay, so any way you write it is going to be correct. All right, let's move on. So I've created some multiple choice questions to kind of help us go through some of these periodic table unit sorts of questions. And typically the Regents exam will ask you, I'm going to say maybe a handful, not many. So really take your time with them, look them up, and don't lose the points that are free. All right, so let's take a look at your periodic table questions. So these I pulled from the last few Regents exams. So let's just go through a few of them to see if we can get some practice. So number 1 says the elements on the periodic table are arranged in order of increasing. All right, this question you should never get wrong. It is the atomic number. So don't get that question wrong. All right, so the atomic number is how the table is arranged. Number 2, So which list of elements consists of a metal, a metalloid, and a nonmetal? So here's that example. So again, make sure you know the metalloids because those are the ones that are going to be important in trying to determine whether something is a metal versus a nonmetal. So if we go through, so lithium, I'm going to go back and forth between this and my table. Lithium is here, so that's a metal. Sodium, right underneath it, that's also a metal. So we can actually cross off this one because there are metals in there, more than one. Let's look at number 2. Cr, metal, Mo, underneath that, that's also a metal, so we can get rid of that one. Let's look at Sn, which is here, so that's a metal. Si is our metalloid, and our last one, carbon, is a nonmetal. So it looks like that is your answer. There's your metal, nonmetal, and metalloid. Okay, right there. Number 3, which list includes elements with the most similar chemical properties? So we talked about in the review that most similar chemical properties are found in the same group. So you would just go again, look at your reference and see which ones are in the same column. All right, so let's look at choice 1. Bromine is here. And let's see if Ga is in the same group. It is not, so we can get rid of that one. Cr, Pb, and Xe. Cr is here. Pb is not in that column, and neither is Xe, so we can get rid of that one. Os and Ce, I'm sorry, Os and Se. Os, Se, they are in the same group, therefore they have the same or similar chemical properties. In case we don't get through most of these, I do have the answers on this sheet, so you're welcome to download it. It's in the instructions, or not the instructions, the description of the course. I've given these documents to you in case you want to try them on your own. All right, so number 4, the elements in group 2 are classified as. So group 2, they want you to know, do you know groups or columns? And they want to know, do you know what side table this is? All right, so group 2, those are your metals. So you are metals, there you go. Number 5, compared to atoms of nonmetals in period 3, the atoms of metals in period 3 have. Compared to the atoms of nonmetals in period 3, to the atoms of metals in period 3 have. All right, so the question is a little bit confusing the way it's written. So let's go through it one by one. So nonmetals in period 3, so period 3 means this row here, nonmetals over here. And the answer choices are talking about electron shells and valence electrons. So let's compare them. So if we look at period 3, the nonmetals have 7 valence, the metals have 1 valence. Let's see if that comes across. Compared to the atoms of nonmetals, they would have more electrons, valence electrons, which they do. So we can take choice 2, atoms of metals in period 3. Compared to the atoms of nonmetals in period 3, the atoms in metals in period 3 have. So the metals would have fewer valence electrons. This is basically asking you, do you know that the period contains the same number of principal energy levels? So you can get rid of 3 and 4 and then compare valence number. Please don't make the mistake that I did as reading it. I read it again to make sure that I answered a question. They want to know what the metals have. The metals would have fewer valence electrons than the nonmetal side. All right, number 6. If an element X can form an oxide that has the formula X2O3, then element X would most likely be located on the periodic table in the same group as. All right, so let me pull up my pen so we can talk a little bit about this. So X2O3 is a chemical formula, all right, and they're trying to figure out, well, what X could possibly be. So let's use our crisscross method to kind of figure out what the charge of X would be, and then we can figure out what group it would be in. So we know that oxygen, right, if we crisscross backwards, is a -2, which means that X had to be +3. So if we look at our reference back onto our periodic table, we're looking for group 3, right, or 3 valence electrons, or a +3 oxidation state. So that seems to be group 13. All right, so see all the +3s. So in the question, they want to know, well, which one could that possibly be? So barium, Ba, Cd, In, or Na. So Na is in group 1, Ba is in group 2. Let's see, In or Cd. In is in group 13, so it could be In. Very easy question, okay? Right, number 7, at STP, which element is a good conductor of electricity? So a way of asking you which side is, or metals, so, or which one of the following is a metal. So a good conductor of electricity. So chlorine is a non-metal. And in case you didn't know the symbol, you can look it up on table S, but here's chlorine, non-metal. Iodine, also a non-metal, that's I. Silver is Ag, which happens to be a metal. That's probably our answer. And sulfur is a non-metal over here, so it is not going to be a good conductor. All right, number 8, in the formula, XF2, the element represented by X can be classified as, all right, so again, the same idea. We can use our reverse crisscross to help us here. And let me just zoom in on so I have a little bit more space to show you. So if we did XF2, right, we know fluorine is a -1 charge, which means this had to be +2. So which elements have oxidation states of +2? And that is group 2 of metals right there. Good. Which element has the highest melting point? I know originally there was a question about the trend for melting point and boiling point. I'm going to say not to worry about that trend. Just look them up. But the trend happens to be as you move to the middle of the table, you have higher melting points, higher boiling points. But I wouldn't worry too much about it as you're doing it. Just look up the numbers. So you can look up each one and figure out which one has the highest melting point. So for our purposes, I'm not going to bother. You can look up the answer at the bottom. But you would use table S, get the melting points of each, look them up, and then decide which one is the highest. Okay. Number 10 is showing you a question about allotrope. So again, they're not going to ask you to know the term allotrope, but which phrase describes the molecular structure of properties of 2 solid forms of carbon and diamond and graphite. So they're going to have different molecular structures, and if they have different molecular structures, they must have different properties. Your answer's 4. All right, again, number 11, the element sulfur is classified as. So again, you'd use your table. Here you'd know it definitely would get rid of your metal choices. So sulfur is not in group 18, so it is not a noble gas. So sulfur is right here, which happens to be a non-metal. Number 13, which statement explains why neon is a group 18 element? Right, neon is in group 18 because of its valence number. So the groups are arranged by valence number. So group 18, they have a stable electron configuration. 14, talking about a metalloid, you can pick that one up. 15, which element is a liquid at STP? So bromine is your liquid, but let's say you forgot. What you can do is you can look up melting points and boiling points of each and find out which one has melted but not yet boiled, and it's going to be bromine. You could do the same thing for number 16, which element has the greatest density at STP, right? Density is given to you on the list on table S, so just go and look them up, right? Write them down and compare them. So we won't go through that one. 17, a 10-gram sample of which element has the smallest volume at STP? So this question was a little bit tricky, so I want to just go through it with you. So we know if they're talking about volume and they're giving you a mass, most of us should be thinking about, or you should be thinking about, is your density formula. So D equals M over V, right? Mass and volume. They're asking about mass and volume in the question. So they want to know which one's going to have the smallest volume. So what you can do is you can look up the densities and use the mass amount and then do a quick little calculation to find out which one will have the smallest volume. So let's just pick one off for example. As an example, let's do aluminum. Very quick. I don't think I have a calculator in front of me, but we'll go best we can. So let's look up aluminum. Here's aluminum, and the density for aluminum is 2.7. Okay. So 2.7 equals the mass, which was the 10 grams, over X. So you end up cross-multiplying 2.7x equals 10 grams. You divide by 2.7. So you just go through each one and figure out which one has the smallest answer. All right, a couple more questions just to get some review. The number of valence electrons in each atom of an element affects the element's, we should know, never get it wrong, chemical properties, valence number. The valence electron of which atom in the ground state has the greatest amount of energy. So this has to deal with your electron configurations. So the valence electron of which atom in the ground state has the greatest amount of energy. So it's going to be the one that is in the furthest away, or the greatest number of energy levels. So they're asking me about cesium, lithium, rubidium, and sodium. So let's just look up, those are all here in this group, cesium, rubidium, lithium, and sodium. So they want to know which one, as far as valence, has the greatest amount of energy. It's the one that's in the furthest shell. So it looks like it's going to be cesium, if cesium is one of our choices. Yeah. All right, 21, which ion has no electrons? I'm not really sure why I threw this one in here. This is more of an atomic, but you would just go to get the number of electrons, right? It's the proton number is equal to the electron number, except when there's an ion, and because there are positive numbers, that means they're losing electrons. So hydrogen has 1 proton, 1 electron in the atom. If it loses the electron, it now has 0, but that's more of the one before it. 22 is comparing lithium atom to a lithium ion. So when an atom of lithium loses an electron, the atom becomes right? So when it loses an electron, it becomes a positive ion. And the radius is going to be positive ion with the radius smaller than the radius of the atom. This one's number 3. 23, you can look up table S, so nice and simple, all right? Let's move down to some of the trends just so I can show you how to answer these questions. All right, which general trend in first ionization energy and electronegativity values are demonstrated by group 15 elements as they are considered in order from top to bottom? So again, not something to memorize. Go to group 15 and pick 2 elements. So let's pick nitrogen and, I don't know, somebody at the bottom. Let's pick arsenic or something. Look up the values that they're asking you and then just compare them. Did they increase or did they decrease? So if you did memorize the trend, as you go down, ionization energy and electronegativity decrease. Right. So let's take a look at some constructive response since we're running low on time to make sure we get there, because this is where people want to gain their points. So explain in terms of atomic structure why group 18 elements on the periodic table rarely form compounds. So in terms of atomic structure, right, atomic structure means protons, neutrons, electrons, energy levels. Why the elements in group 18 rarely form compounds? Well, rarely form compounds mean why are they unreactive? So based on atomic structure, we'd explain this as they have a full valence shell, or they have a complete, or they're complete valence electrons, or they have 8 valence electrons would be enough to answer your question. All right, let's take a look at 2 through 4. The diagram below represents 3 elements in group 13 and 3 elements in period 3, and their relative positions on the periodic table. So they're given to you. Some elements in the solid phase exist in different forms that vary in their physical properties. For example, at room temperature, red phosphorus has a density of 2.16, and white phosphorus has a density of 1.823. Identify one element from the diagram that will combine with phosphorus in the same ratio of atoms as the ratio of aluminum phosphide. All right, so here's aluminum combining with phosphorus. They want to know what other element on the table would be a 1-to-1 ratio or form a compound that way. It'd be anybody in this row, in this column, right? Gallium or IN would form a 1-to-1 ratio with phosphorus. Compare the number of atoms per cubic centimeter in red phosphorus with the number of atoms per cubic centimeter in white phosphorus. All right, so they're just comparing atoms. The atoms are going to be the same, right? They're the same thing. And 4, consider the period 3 elements in the diagram in order of increasing atomic number. State the trend in electronegativity. So period 3 means going across the row, increasing atomic number. What happens to the trend? So what you can do is you could just take period 3. You could pick sodium, pick chlorine, see what happens, but the electronegativity is going to increase. All right, let's take a look at one more question here before we sign off. I do want to just pull up an old Regents to show you some of the questions that you can, that were on the January exam, but there's not a lot. And this is getting quite boring, I'm sure. So before atomic numbers were known, Mendeleev developed a classification system for 63 elements known in 1872 using oxide formulas and atomic masses. He used an R in the oxide formulas to represent any element in each group. The atomic mass was listed in parentheses after the symbol of each element. A modified version of Mendeleev's classification system is shown in the table below. This gave a lot of students trouble that year this question was given. So they give you Mendeleev's table, and they're just showing you some oxide formulas. So let's look at the questions. Says, explain in terms of chemical reactivity why the elements in group 18 on the periodic table were not identified by Mendeleev at the time. So group 18 were not discovered by him because they did not form oxides, all right? They were unreactive. So group 18 elements don't react with other things, so Mendeleev would not have found them because they were unreactive. So the question tells you to explain in terms of chemical reactivity. What's nice about this is kind of focusing you in on how to answer it. So there are only two ways to answer this. You're either reactive or you're not reactive. So because they're not on the table, they're not reactive with oxygen. Number 6 says, based on table J, identify the least active metal listed in group 1 on Mendeleev's table. So this is a very simple question. You would look at the group 1, which is the column here, and then you'd use table J on your reference to find out which one was least active. So table J, let's scoot up. Where are you, table J? Here you are. And you just find most reactive metals are at the top, least reactive metals are down towards the bottom. So identify a metal that is least active metal listed. So you just compare these and figure out which one is towards the bottom of the table. And then number 7, based on Mendeleev's oxide formula, what is the number of electrons lost by each atom of the elements in group 3? So group 3, you can use your oxide formula to help you. So here's your group 3, R2O3, so minus 2, which means plus 3. So that means everything in this group has lost 3 electrons. All right, identify one characteristic used by Mendeleev to develop his classification system. So you can read here, it says he used oxide formulas, but he also used atomic mass, right? So I'm gonna stop there as far as our questions go, because you can answer these questions on your own, and I'm just trying to give you a quick little overview. But let's just check on some questions to see if I've answered everybody. So Danny's asking about an oxide formula. So let me just go back up to this problem. An oxide formula just basically means something that reacted with oxygen in an ionic sort of way, all right? So oxide formula here, right, are all on the top, and I'll highlight them for you. So these are the oxide formulas. Just something that reacted with oxygen is an oxide formula. Okay. All right, let's check on some more questions. Let's see. Can you please go over the question with the AL short answer number 2? Let's see. I'm not sure if this is the one you're talking about. I think this is the one you're talking about. I'm not really sure what you mean by AL. Yes, okay, so let's go over that one. So it says, identify one element from the diagram that will combine with phosphorus in the same ratio of atoms as the ratio of aluminum phosphide. So let's actually go, so they're giving you in this problem, so here's your phosphorus. So phosphide, all right, is the second part of your chemical formula. So it means that you have either aluminum, Ga or In combining with phosphorus. So what you can do is you can use your periodic table to help. So let's go and take a look. So what's nice about this is that you can find phosphorus in the table, and I'm going to highlight the one that they're actually, the piece that they gave you. This is the piece of the table that they listed for you in that diagram, okay? If we look at phosphorus, phosphorus is a -3. So when aluminum combines with phosphorus, so Al, aluminum is a +3. So when you form the compound aluminum phosphide, the charges are already balanced and equal, right? Meaning that you would need one aluminum that has a +3 charge to balance out one phosphorus that has a -3 charge. So the ratio is 1-to-1. So your teacher might have shown you crisscross, and let me just clear this off so I can get a little bit bigger for you. Let's go with a whiteboard. Let's clear the strokes. Okay, so your teacher might have shown you crisscross, which means this would be a 3 and this would be a 3, and I'll write it out this way for you. And then you would reduce, so your ALP would exist. So you want to know who would react in the same way. So in the same way, whoever's going to have a +3 charge is going to react in the same manner. All right, so let me clear this off and pull back our question. So the ratio wants to know who's going to combine the same way. So either one of these is going to do the same thing because each of them has a +3 charge. So the only one that would not work would be your silicon, right? Because your silicon has a -4, right? So it's not going to form a compound with phosphorus in that manner. Hopefully that answers your question. All right, let's look at some other questions coming in before we run out of time. All right, I answered the oxide formula. I answered short number 2. Was the next video removed? Caitlin, I don't think so. So hopefully it comes through. Should be going shortly. Maybe they're getting themselves ready. Okay. So I think I'm going to stop there because the periodic table is a pretty straightforward review. Give you guys a little bit of break. Hopefully you're finding this helpful, and that you should also give these teachers that are participating a real round of applause, because we're really putting in this extra effort to make sure that you guys do well on Tuesday. We really want you to do well. Keep in mind, chemistry is not difficult. The exam, even though it's going to seem hard, keep it simple. Answer your short answers in a simple way, all right? And your multiple choice, go through it. Don't second guess yourself, all right? The exam doesn't try to trick you, and that's what's good about the chemistry exam. I think there's just one more question. Let me just see before I log off from you. What's the link for the next video? It's been removed. Actually, while I have you guys here, let's see. See if I can help you. Let me pull up the links. I'm sure this person has probably just maybe quickly edited it, but it should be coming up soon. So if it doesn't start right at 1, it should be there shortly. Okay, so hopefully, let me just stop sharing my screen and say goodbye to you all. Hopefully you found this helpful, and keep watching. Congratulations on those of you that are participating in the live forum. It's actually worked out really well, and I hope it's helpful. Keep in mind that you can watch these videos anytime after this. It's not going to be live, but you can watch it to review. And good luck on Tuesday, and I really hope you guys hope you do well. All right. Again, just hold on for the next video. I'm sure whoever is presenting is probably just doing a quick little fix on it or something. So just hang on for it, and if it doesn't start immediately at 1, it will be there. So I think I put the link, the page for the Google Doc in the not the comment section, but the description section. So just wait, and hopefully it goes up. If not, I'm not really sure. All right, but I'm sure somebody will have it there for you. Good luck to you, and congratulations on those of you that watched. Good luck to my class. Hopefully you guys do well over at Bayshore. I'm pulling for you. I'm very excited, and I'm really looking forward to a good outcome on the exam, okay? All right, thanks guys.